Okay, hello everyone. My name is Zavier from Nalco Water, Taiwan. Since today we don't have too much time, so I will introduce the history of the Nalco Water in Taiwan quickly, and to save time to the following section and technologies part. So Nalco Water started a journey in Taiwan in 1988. Originally, we are focused on providing the water treatment technology for chemical industry, including the boiler water and the cooling water and the chemical cleaning. Okay, so our target customers like the petrochemical, steel, and manufacturing, especially like the CBC, Formosa Group, and China Steel. Okay, in the 2000s, Nalco established the formal subsidiary in Taiwan. We call it Nalco Taiwan Limited. At that time, we also expand our service into the electronic and semiconductor, food and beverage, and biotech. And also in 2011, Nalco was acquired by Ecolab. So now you can see we have like our name is like the Nalco Water and Ecolab company. Yeah. And we also deploy either 3D tracer technology in Taiwan. 3D tracer is the digital smart water management system. And so currently we also use this technology in our petrochemical customers. Okay. So from 2023 until now, we focused on the geothermal water treatment. Also, we also leveraged our global development experience, also replicated the successful case in Taiwan. So while everyone is focusing on exploration and drilling, you can see, but based on our past operating experience, we noticed that the scaling and the corrosion will impact the geothermal power plant efficiency. So that's why today we want to share our technology with you. Yeah, that is the introduction. So the next one, my colleague Fritz will introduce the technology in detail.
Thank you. Good morning, everyone. So the title of the presentation is Understanding Geothermal Chemistry. So potential chemistry-related challenges after drilling. So you have drilled your wells. So you already drilled your wells. You already put up your plant. So what happens next? So the goal is to maintain the output, right? So we have seen wells, for example, wells at, let's say, 10 megawatts in a span of 6 months, completely shut because of mineral scaling. So you can see here that the difference between geothermal and conventional power is for geothermal energy, you have to use of whatever fluid that you will find downhole. And normally, these fluids are saturated with minerals. That's why we need to understand geochemistry because it affects how we will utilize the plant. So it is believed that mineral scaling is one of the biggest challenges in terms of utilization for a geothermal facility. So it's one of the biggest limiting factors. And what we want, since we know that geothermal is a sustainable source of energy, what we want is how can we further reduce the cost? How can we make this more sustainable? So this is where management of mineral scaling comes in. Not just mineral scaling, but also corrosion challenges. So the key word here is prediction. Prediction and prevention of possible geochemical challenges are critical in maximizing the output of your geothermal facility. Okay, don't be surprised, don't panic. This is the second time in a long time that you've seen a periodic table. Okay, so these are the common elements that you will see in a geothermal brine. So it's a cocktail of elements. So you have sodium, potassium, magnesium, calcium, manganese, iron, aluminum, silicon, is one of the most common minerals that we're seeing. Also, now we are seeing a lot of arsenic and antimony. And there are various factors influencing scale formation. And we can narrow it down into three. So first is temperature. There are minerals that are more soluble in hot environments, in high temperature environments, and there are minerals that are more soluble in lower temperature environments. Also, chemistry profile. Of course, scaling is a function of mineral concentration. Some scales are dependent on pH and also chemistry interaction. So some elements compete with another element, forming another type of mineral, and also some minerals combine with another mineral to form a much harder mineral, a much more challenging scale. And reaction and induction time. So this is a typical flash binary plant. So we know that the hottest part will be at the production well, because this is our source, the reservoir. So the second, the production well is the highest temperature one, and then going to your reinjection systems, either hot reinjection well or cold reinjection well. What can we say about the temperature profile? So as we go from the production well to the reinjection well, of course, temperature declines. And we know that temperature is a factor in mineral scaling. Pressure declines, and if there is decline in pressure, there is what we call flashing, right? So what we get from production wells in liquid-dominated systems sometimes are, most of the time are two-phase fluids, combination of liquid and steam. So if your pressure continues to decline, part of that liquid turns into steam. What happens with the minerals in your liquid phase is it becomes more concentrated. And concentration is a factor also for scaling. So the scale formation in geothermal facilities can be summarized into 4 steps. First is achievement of supersaturation. So your system needs to be supersaturated first for scaling to happen. That's why we have this term called saturation index. So saturation index, we calculate what is the scaling tendency of a particular mineral. If your saturation index is less than 1, meaning it will not scale. If your saturation index is equal to 1, meaning it is saturated with respect to your solution, there is possibility of scaling. And if your saturation index is above 1, it means that your system is oversaturated. So higher than you're almost sure that it will scale up. So your conditions should achieve supersaturation, and it will start with what we call nucleation. So there will be like small particles in your system, and it will act as seed for your minerals to grow, or for your scales to grow. And then your crystals will grow, and then when it's big enough, it will precipitate out of your solution, and you will see the white deposits that you see in your pipes. So these are the scale build-up. And we know that in geothermal, flow is directly proportional to output. So if your pipe is blocked, your flow goes down, your output goes down. So this directly affects your output. So what we do is we developed a software called Geomiser. So this is a modeling software specific for geothermal. So we input mechanical, operational, and chemical parameters. And it will predict at what part of your plant scaling could potentially happen and what scale. So it will be able to generate a saturation index versus temperature plots, for example, of silica. For example, here, this is arsenic sulfide. So it will be able to identify what scale will form and at what part of your plant. So production well scaling, I think this is where the case of Taiwan will be. I mean, the scales that the scales that I will show here is more applicable to the cases that you have here in Taiwan. So our team were able to analyze some of the wells, some of the existing wells, and we can confirm that there is challenges in terms of calcite scale formation. So crystalline calcite or aragonite. So calcite is calcium carbonate. So this one, it has a retrograde solubility, meaning it is more soluble in lower temperature and less soluble in higher temperature. So in that solubility, where do you think calcite usually forms? It's in the production. Yes, it's in the production well. So it is the solubility is lowest in your production well, in your hottest zone. So what happens is, so before you bring your fluid to the surface, it is still single phase. As your fluid rise up, so your CO2 is being released into the solution, and what happens is your pH increases. So calcite is more soluble in acidic conditions. But once you release the CO2, it becomes more basic. It becomes more alkaline. So it pushes the reaction forward. It pushes the reaction forward, forming more calcite deposits. That's why, anhydrite is calcium sulfide. It is same deposition behavior with calcium carbonate, but this one forms in high temperature regions. It is not dependent on pH. So usually you see anhydrite in the deepest portion of your well. So typical scaling location is in your production well, here at the flash point. So what we do is you incorporate your treatment method when you do your well design. So usually the way we address calcite, if we are going to use an inhibition system, is to dose an anti-scalant before the flash point. So you dose the solution before your fluid flashes so that it can be incorporated in your fluid. So aside from calcite, three major scale formation in geothermal are silica, which is very common, metal silicate, and metal sulfides. So silica in itself, it is soft. So if you see amorphous silica, it is white in color and it's very soft, and you can easily remove it using water jet. But in some fields, they are expecting silica scale, but they're getting hard. Hard scales, the color is gray. So what is the meaning of that? So most probably, that scale is combination of silica and metal ions, forming metal silicates. So you see, amorphous silica alone is easy to manage. It is easy to remove. But if you have metal silicates, the morphology changes, it becomes harder. So silica is dependent on temperature, pH, and concentration. So it is more soluble in higher temperature. That's why it is not common to see silica scaling in production wells. You often see silica scaling in reinjection wells and also in binary systems. So in binary plants, in your preheaters, in your vaporizers, you can see silica scaling. So metal silicates, iron silicate, same behavior with amorphous silica, but magnesium silicate, it's different. It is less soluble in high temperature environments. That's why in systems where you have intrusion of cold water, you can see smectite, which was mentioned in the presentation earlier. So this one is also pH and temperature dependent. And metal sulfides, if your system has high H2S, there is high tendency of metal sulfide formation. So how does silica deposit? So it starts with monomer. So the way silica deposit, we call it polymerization. So it starts with monomer, silicic acid monomers. It will form into polymers, and then it will grow and grow until you have silica colloids. So this is still not visible to the naked eye. And then these colloids will aggregate, and then once it is heavy enough, it will drop into the solution, forming your scales. So, yeah. So how do we inhibit silica? How do we manage silica scaling? Common method is called pH modification. So you add acid into the solution to delay the polymerization. So the polymerization of silica, it is catalyzed by hydroxide ions. So hydroxide ions, so if your system is near neutral to slightly alkaline, so you have a lot of hydroxide ions. So what happens is your acid gives a proton into this solution and neutralizes your hydroxide ions. So it delays the polymerization. But the challenge is in acid treatment, you have a very small window. So slight addition of acid can shift your pH drastically. And if you have too much acid, it contributes to corrosion. If you have less acid, it contributes to scaling. So you need to balance that one out. And we have seen that in some treatment facilities that they're doing pH mod, they tend to form metal silicates or iron silicates and iron sulfides. So you are possibly addressing silica, but you are creating another type of scale. So that is the challenge for pH mod. Another one is the use of polymer inhibitors. So you incorporate the inhibitor in the polymerization phase. So you incorporate the inhibitor here so that the monomers will not form polymers. So those are the two chemical strategies to address silica. Next is corrosion management, which is a common issue as well in geothermal, especially in areas where the fluids that you have drilled are acidic. So there are different drivers: process conditions, of course, temperature, pressure, and changes in conditions. So we know that temperature, corrosion rate is, if not directly proportional, so it is exponential in terms of temperature. Process constituents, so high salinity, high suspended solids can also be factors in corrosion, and it can affect both your wellbore and your surface facility. So there are different types of corrosion. Common in geothermal will be general corrosion, pitting corrosion, and also stress corrosion cracking. We have seen this one, flow accelerated or flow enhanced corrosion. And the types of corrosion based on corrodant: sweet corrosion driven by CO2, sour corrosion driven by H2S, acid corrosion driven by HCl. So as I've mentioned, this is being affected by temperature, pH, of course, salinity, and the corrosion products. So, okay, so corrosion reaction, it's a redox reaction. So in normal conditions, your pipe will form a protective magnetite layer. So this is iron oxide. It's the what we can say the natural passivation film of your system. So if it is being subjected to different factors like turbulence, changes in pH, H2S, your magnetite layer is being transformed into another type of iron and oxygen containing compound, which is hematite, and in some cases, derivatives of iron oxide. So some of the approaches that we use, same with how we address silica, we use adjustment in terms of pH, but now we're using caustic. We raise the pH of the well to become less acidic, but the drawback of that is you are introducing another problem, which is scaling. So we know that scales are pH dependent. And another one is the use of filming amines. So you dose corrosion inhibitors or filming amines in your system, and it creates a passivation film on the walls of your pipe. And the benefit of that it prevents your corrodants into getting into the surface of your pipe. So it's a protective layer to prevent or lower corrosion rates. So, yep, that's all for our presentation. I hope you were able to learn something about mineral scaling and corrosion. And I know that Taiwan is very aggressive in their geothermal prospects, and we believe that prevention is really the key. And we are here to help in modeling and simulations. Thank you.